All right, so this evening we're going to cover Module 2. We'll go through some of the material on OLI and hit the key points, the key things that you need to know moving forward, and hopefully things that will help you on quizzes 3 and 4 that are due. I set those due dates on Tuesday because the assignments went up. Late. I had them ready, but I forgot to open it up. It just sort of escaped my mind, and then one of your colleagues reminded me. All right, so let's go through and talk about Module 2. Module 2 is kind of where we get into describing data information. If we move forward, we have some steps and statistics. We produce the data, that is, we decide what we're going to measure and collect the data. We did that in the previous module. Now we're going to explore the data, that is, we're going to analyze and summarize the data. As it says, this is also called, right there, exploratory data analysis. So that's what we're going to do in this module, is once you have a bunch of numbers, what do you do with them? Okay, well, let's first of all talk about data. Data, as it says, consists of individuals and variables variables that give us information about those individuals. And individuals can be an object or a person, and a variable is an attribute, such as a measurement or a label. So here's a data set from a medical study. The individuals are the patients, which are listed on the left-hand side, labeled only by number. And it looks like these are women who are giving birth, and it has the age of delivery, the weight of each woman prior to her pregnancy, whether or not she was a smoker, the number of doctor visits in the first trimester, that is in the first 3 months of pregnancy, race, and birth weight. So each of these labels at the top here is a variable. A variable is something that can that's going to take on a different value for each individual. It may be the same for two different individuals, but in general it can vary between individuals. Let's see who we had join us. Kimberly, welcome to the webinar. Kimberly, we have only just, that's okay. There's no requirement to be on time. We have just started. We're looking at page 25 in OLI if you want to follow along, but I think the audio and video is working a little bit better tonight. So you may be able to just follow along on your screen. So right now we're talking about some variables. As this says, there's 6 variables that list them. And it also gives the values for each variables or the units if they're numbers. So like the mother's age, the units are years. Mother's weight, the units are pounds. Whether mother smoked during pregnancy, well, it's yes or no. Number of doctor visits, obviously that's just a count. Race, there's different variables for that, values for that, and then the baby's birth weight in grams. All right. This simplifies things a little bit. There can be more than 2 types, but there's 2 principal types anyways. Quantitative, which are numerical values. Notice it says, this is kind of important, numerical values that can be averaged. And a quantitative variable is frequently a measurement. It could say or a count. It's a measurement. It's often a measurement or a count. And then categorical variables have values that are labels. A categorical variable puts individuals into categories. So of the ones up above, the quantitative are age, weight, number of doctor visits, and baby's birth weight. Categorical variables are whether the mother smoked and the mother's race. The important thing about the fact that it says numerical values that can be averaged is there are some numbers, some possibilities for variables that are numbers but wouldn't necessarily be quantitative. An example of that would be someone's zip code. That's not a measurement of anything. It's not a count of anything. It's really a label. It's associated with where you live. So zip code is actually a categorical variable, even though it's a number. It wouldn't make sense to take an average of the class's zip codes. That wouldn't really give us a whole lot of useful information. So, but by and large, quantitative is numbers and categorical variables or labels. So then they give, in fact, here's one where they do have zip code, and so that would be categorical, and then they go through and do some others. Now, notice in this one, the individuals described, in this case, there's a random sample. Here's part. It looks like people living in the U.S. in the year 2000. And then each of these is a variable. So in this case, Florida would be categorical, or state would be categorical, zip code would be categorical, family size would be quantitative, average income would be quantitative. So even though zip code is a number, it is still categorical because it really labels people by location. All right, and then that's just another exercise. All right, so that's just kind of getting you used to the idea of what data is. So in this section, now we're going to start organizing data, and one way we can do that is what's called a dot plot. And we'll just go down, and so this is a graph of different cereals and how many grams of protein each one has. And so this is just each cereal labeled. They're put in alphabetical order, and each bar is how many grams of cereal there are in that particular cereal. It tells what the name of that graph is, but that's not important. We won't be looking at this kind of graph very often. And then here, we have a different graph of the same data. And by the way, the word data generally is plural, so if you hear me say data are, or refer to data as plural, that's because the word data generally is plural. So now we've got you can see here more of a pattern. You can see most of the cereals that we looked at have only 1 or 2 grams of protein. There's only 4 cereals with more than 2 grams of protein, and even then it's just 3 or 4, except for one kind of out. This value here, the 6, we might call that an outlier because it's much further. It's very far away from where most cereals are. And in general, when we're looking at graphs, we're looking for those sort of notable characteristics. So we might look to see, oh, are there any points that are outliers that don't really follow the pattern of most of the cereals, and that's one of them. And then here, as this says, here are some observations, and we've already mentioned these. The amount of protein varies from 1 to 6. Most of the cereals have 1 or 2 grams. Larger amounts of protein are less typical. One cereal has 6 grams of protein. This much protein is unusual for this group of children's cereals. And those are good summaries of the data. And so here's graph A. In this case is another dot plot. The dots are squares, but that's okay. And then again, here's a dot plot versus a non-dot plot. Dot plots in general are good. And then there's some questions about being able to interpret the data that you see in the graph. Okay. All right. So now, when we're looking at a dot plot, let me make this a little bigger. We're looking at a dot plot. We're looking for some certain characteristics of the data, and there's 4 main ones. If you look at the in-class notes that I post online, this is also there. Shape, and center, and spread. And then the last thing is we look to see if there are any outliers. Okay, so as it says, you see in this little graphic here, shape, center, and spread describe the overall pattern, and then outliers are things that deviate from that pattern. So what do we mean by this shape, center, and spread? How do we describe that based on by the picture? Okay, well, let's start with shape. If you look at these 2 graphs, one is a graph of sugars in cereal, and the other is a graph of exam scores. What you sort of do is sort of trace a smooth curve over the tops of the bars, and that can help you determine the shape. The one on the left has its peak on the left-hand side, and then it tails off to the right, but not very far to the left. Okay. Well, that long tail tells us the shape of that graph is right skewed, or sometimes skewed to the right. Whereas this one, there's a peak in the middle and then it tails off pretty evenly in both directions. And a lot of times we call a graph like that bell shapes. So here are the common distributions: right skewed, that was the sugars one. Left skewed would be the other way. So, and this is an interesting graphic. This is cereals marketed to adults, and you see most of those are somewhat low in sugar, with sugar dropping off fairly rapidly as you increase. So that's right skewed. But for children, the cereals tend to be have more sugar, and then they trail off more to the left, so that's skewed to the left. So basically, the direction of the skew is the direction of the long tail. I hear someone beep in. Oh, yay, Paris has got his thing working. Yay, good deal. That's good to hear. All right. Okay, so long tail to the right, right skewed, long tail to the left, left skewed. And then symmetric with a central peak is bell-shaped. So these are a couple of examples of bell-shaped. With children's cereals, they're very, very closely clumped together. But they are bell-shaped. There's one central peak, and there's pretty even on both sides. The adult cereal is also fairly bell-shaped. Central peak, and it tails off pretty equally in both directions. Uniform would be something that's more or less flat across. There's not a tail in either direction. So here's an example. Here's the last digit from 47 students' telephone numbers. The distribution is fairly uniform. There's some that are lower and some that are higher, but overall there's no discernible pattern. We expect uniform basically means all of the values occur roughly the same amount of time. All right. Also being able to sort of predict what shape a distribution might have is useful, and that's what this question is. I realize now, by the way, I'm using Chrome, and Chrome does a much better job of increasing the size of these questions. So like, for example, it says a repeated volume measurement of a 1 liter bottle of soda. Well, we expect those all to be close to one central value, and this is not like that. Quiz scores on a very easy quiz where you would expect most people to be high and just a few to be low. And then salaries of the New York Yankees in 2010. That might be harder for you. You may not be sure about that one. But these, basically, we're looking for something where almost everybody is fairly close together at the high end, and then there's just a few towards the lower end. And baseball salaries don't tend to be like that. They tend to be a little more spread out, with a few very, very high, and then maybe some more closer together in the middle to the lower end. And so if you clicked salaries, for example, it would say it'll be skewed to the right. There are a few superstars that make a lot more money than the rest of the team. So, but quiz scores. On a very easy quiz, we expect most students to do well. All right. I'll save that for you. So that's shape: right skewed, left skewed, bell-shaped, or uniform, or some of the ways we describe shape. Center and spread. For center, we're looking kind of at a typical value, or sort of the middle. It's at this point, it's just sort of kind of looking at it and guesstimating. And then spread is talking about the variability. So you can talk about the overall range, which is the largest minus the smallest. And then also you can talk about the typical range of typical values, which is where most of them are. So these are the sugars again for adult and children's cereals. You might say, and so we already talked about the shape. Adult was right skewed, children's was left skewed. But now with the center, it appears that for the children's cereals, that the center is kind of just maybe around 12 grams of sugar, whereas for the adults it appears to be maybe around 3 grams of sugar. And so that would be looking at the high bar for the adults, and then the high set of dots for the adults, and the high set of dots for the children. All right. So a typical adult cereal has 3 grams of sugar, and a typical children's, that's exactly what we said. And then the spread, their spreads are pretty similar. The adults goes from 0 to 14, and the children's goes from 1 to 15. So they both have a range, overall range of 14 from lowest to highest. The adults, the typical values tend to go from, say, maybe 0 to 8. And for the children, it's kind of 8 to 15. So also the typical range of values, those are pretty similar. And then so they have an overall range. Typical adult, they said 0 to 6, we said 0 to 8. For the children, they said 9 to 13. So we changed it a little bit. All right, and you can read a little bit more about that. At this point, this is all what we say qualitative. We're not calculating anything. We're looking at the graph and kind of making our own judgment about it. Okay. And then they're telling you to compare shape, spinner, and spread for the distribution of calories in adult and children's cereals. And so you type in your answer and you click your submit and compare and see maybe what the authors say is a pretty standard answer. All right, and there's some more problems. And then lastly, outliers. It says outliers are observations that fall outside the overall pattern. So you're looking for values that are much higher or lower than typical values. So look at these values here. These 2 dot plots, these are wrist measurements. They show the man with the lowest wrist measurement here at the bottom in yellow. Well, there's other people who are not too far above him, so we probably would say he's most likely not an outlier. But these 2 women at the high end, they probably are outliers because there's a considerable amount of space between the rest of the women whose wrists were measured and those 2 women. So just because a value is at the end, it's not an outlier necessarily. The low one may be an outlier because bulk are in a fairly narrow range. This one at 13 may or may not be an outlier. And again, that's another thing where right now we're kind of making judgment calls, but as we move forward through Module 2, we'll see how to do these things numerically. All right, so another exercise. And then now we're going to switch from dot plots to histograms. Now, with dot plots, a weakness is it has several weaknesses. When it works really well. You can see all the individual data values. Each dot represents one individual. But when it doesn't work is if there's a lot of observations, you get too many dots, or if they're too close together or too far apart, we end up with a dot plot that just is not as easy to use. So as this says, a histogram is another way. Histogram, as it says, again, is particularly useful for large data sets. So here's a dot plot, and it says hip girth. Let's see, for 507 adults who exercise regularly. I'm a little surprised it has such a good bell-shaped measurement because it doesn't distinguish between males and females, but perhaps males and females have similar hip girths, since women tend to have wider hips relative to the rest of their body than men do. But what we do then is we can split the data into equal parts. So here we're making a bunch of parts that are each 5 centimeters wide. So the hip girth is measured in centimeters. So you got, and that's how they do it with the alternating colors of white, gray, and so on. So we've got sort of a bin from 75 to 80 with one individual, a bin from 80 to 85. Now let's see, they count 11. Well, we got 4, 5, and then 6, that's 11. So note that these 2 at 85 are counted in the white bar to the right. And that's usually how we do it, is that we count values that are on the line between 2 bins. And the bin, you could say, it includes its lower end. So this white includes 85, but it doesn't include 90. And the next bin from 90 to 95 includes 90, but not 95. And then the reason why we sometimes do that the most common reason why we do it that way as opposed to the opposite direction is because if we have data that start at 0, you want 0 to be included in your first bar. So the first bar would include its left endpoint of 0 if you had data that started close to 0. And then the numbers at the top just tell you how many dots there are in each of those. So then we translate that to a histogram instead, where each bar, the height of that bar, is how many individuals are within that range. And here's that picture now with bars. So from 85 to 90, if you go back up, 85 to 90, there's 48 right there. And so the height of that bar is 48. So basically the height of each bar tells you how many individuals there were. So in this case, there were 48 people in this sample who had hip girth of at least 85, but less than 90 centimeters. Okay, and I said it specifically that way because the 85 is included in the 48, but 90, someone with a hip girth of 90 centimeters would not be. So we got 48 people who had hip girth of 85 up to, but not including 90 centimeters. And then we had 97 people who had a hip girth between 100 and 105, not including 105 centimeters. Okay. You can still do the same thing with a histogram that you could with a dot plot in terms of talk about the shape, center, spread, and outliers. This is fairly bell-shaped, centered, just below 100 centimeters. Might say somewhere around 95 to 98 centimeters is our center. The spread, well, it looks like we've got an outlier up here. There was one dot that was above 125, so that person might be an outlier. Oop, I got to pop up to do that. And so we might say typical that the spread generally is from 75 to 120. There was one outlier who was above 125. Typical values, maybe you might say, range from 90 to 105, or even you might say from 85 to 110. Again, at this point, it's kind of a judgment call. All right. As it says in a histogram, the count is the number of individuals in each bin. Sometimes we call that the frequency. These were fairly large numbers. If we redid this sample with a different sample size, if we wanted to compare them, it would make more sense to compare the percentages, or sometimes the proportions, giving it as a decimal. And that's what this is, the relative frequency. A lot of times that's more useful to calculate the percentage within each group rather than the total. So the frequency is the count, and the relative frequency is the counts divided by the total. In this case, it was 507 people, I think it said, that was measured. We can go back up here. Yeah, 507 adults. So if we wanted to find the relative frequency for these bars, let me pull up my calculator real quick. So I would just take, like for the first bar from 85 to 90, I would just take 48. I would divide that by 507. So the relative frequency would be about 0.095, or you can convert that to a percent and say it's about 9.5%. So just under 10% of the people in this sample had a hip girth of 85 up to, but not including 90 centimeters. Right, so that's the relative frequency. And it makes it easier to compare groups with different sample sizes. All right. And then there's a little pop-up here. If you have some questions about percentages, you can just click over here on the right, and you get a little pop-up window. You can just go through. It talks about some of the things. If you have some questions about percentages, it's a little extra information there. And then some exercises looking at different histograms. Now, histograms are only for quantitative variables because your x-axis is just that, it's numbers, and that's where your variable measurements are. and your y-axis is where your counts are. So you may think, well, it's really like a bar graph, but it's different because in a bar graph you can put the bars in any order, but in a histogram they have to go in the numerical order. So in this case, when you're thinking about whether a histogram can be used to analyze each of these things, if it's a quantitative variable, then you can use a histogram. If it's a categorical variable, you cannot. So, for example, state of residence, that's categorical, so you cannot use a histogram. And that's what that says. All right. So we'll go on ahead. This shows that you can do histograms with different size boxes and starting at different numbers. So here's some grades. This one just uses intervals of size 20. This next one uses intervals of 10 starting at 40, and the next one uses intervals of 10 starting at 45. Well, probably this middle one makes the most sense in this case because those number grades convert to letter grades quite nicely, right? So 60 to 70 is a D, 70 to 80 is a B, and so on. Whereas 65 to 75 doesn't really tell you what grade someone got. But it changes things a little bit in terms of how it looks. So this is just sort of a picture of how those bins were created from the grades. All right. So here you go. We want to avoid histograms with large bin widths where you only get a few bins, and avoid histograms with small bin widths that have lots of bins. So I would say in terms of a good number of bins, I would say anywhere from 6 to 12 is a good number. That's not a hard and fast rule, but that's a good number in general of bins to have. So let's see here. That moves based on the zoom. So this is kind of nifty. You can change the bin widths here, either by a slider or so I can do a bin width of 20, of 25, of 5, and you can see as the bin widths get narrower, then I kind of lose the pattern until I get to 1, and there's really no distinction whatsoever. And you can actually make the bin widths more finely, so I can do 9, for example, there, and let's see what it says. Oh, and then if you click Show Individual Grades, you get dots under the graph that show you what the individual grades. So in order to do that, you have to have the CDF player installed on your computer. I wasn't able to get it to work with Firefox and OLI, but this is what I'm in now is Chrome, and it seems to be working quite nicely. I don't know why there we go. That one disappeared. All right, so it says use the output to answer these questions, and then a little more on histograms, and then one where you sort of have to think about the pattern of the data, and then what the variable might be. So, like weights of birth of 10,000 babies. Do you think that they're all most of them are heavy, and then there's just a few that are light, or most of them are light and a few that are heavy, or most of them are kind of middle, and then some are lighter and heavier but not equal, or very few are in the middle and lots of heavy and light babies. So you have to think of which of those makes the most sense for birth weights. And then there's three other variables as well. I would imagine that probably one of those describes each of the there's 1, 2, 3, 4. Each one is going to be different for those different answers. All right. Now talking about using a histogram to describe shape, center, and spread, and outliers. This is very much the same as it was with dot plots. Here is a histogram for the ages of the actresses, as it says, who won Best Actress Award from 1970 to 2001. So you got the basic, each bar tells you how many actresses there were in that age range who won the Best Actress Award. For shape, probably right skewed because your peak is on the lower end and you have long tail at the right. Most actresses are young with fewer and fewer as you get older. Center, you would probably say somewhere 30 to 35 years. That's the tallest bar. Spread. Overall, the actresses ranged from their early 20s to their late 70s. I don't know exactly what the highest age is. But the bulk of actresses more typically tend to be from 25 to 50 years old, or even more typically from 25 to 50 to 45. And then there appear to be perhaps 3 outliers: this actress in her 60s, and then 2 actresses in their 70s. So and that's what all of that says. So, and then they give you a paragraph. This is a really nice thing to read through, and I would read through that, and there's going to be some of the exercises that have you do something similar. That sort of thing is good practice, and it's something that I have you do on the test. And then there's a pop-up learn by doing it on a histogram. All right, and then the last one, last page for this, is just some more. Is now using histograms to make comparisons. So like for this one, let's take it as big as we can. So what this is it's the birth weights of women, and you've got one histogram for women who smoke, which is the one at the bottom, and one histogram for women who do not smoke, which is at the top. And these are showing the birth weights. And you can see by and large, the histogram for women who do not smoke is centered at a higher level, and there's fewer women on the low end of the scale as opposed to women who smoke. It's more bell-shaped, but you definitely have more women with low birth weight babies who are smokers. So it's important to be able to look at 2 histograms side by side or any other kind of graph of quantitative data and make a comparison of the distribution. So here I might say, well, it appears that birth weights were less skewed for women who did not smoke, but more symmetric for women who did. And the center was higher, maybe 3,500 grams for women who don't smoke, as opposed to probably more like 2,500 grams for women who do smoke. The spread is fairly similar, although for the 2 graphs, and neither of them appear to have any obvious outliers. And then so they go through that, and then again they synthesize it into a paragraph. So I would definitely read through that in terms of comparing different groups. All right. So and then we have our summary page. That was all topic 2.1. The other topics are a little bit shorter. 2 types of graphs, information about dot plots and about histograms, and then of course you have your checkpoint that you need to do. All right, so that's 2.1, dot plots and histograms. Thinking about shape, center, spread, and outliers. All right, so now we're going to start talking about how to describe these things quantitatively instead of just qualitatively. In other words, can we actually come up with a numerical measurement that can tell us the center, that can tell us the spread, that can tell us the shape, the outliers. Okay, so let's take a look. We're going to start off with center, and that's in red here. Okay, well, one measure of center that we're very familiar with is the mean. Most people know it as the average, but it's the same thing. So I would, so it's just that's the average. We usually write it as this shows X bar, an X with a line over it. On your quiz where it says to do that, there's a video that shows you how to do it in Word. And if you're Word, or if you're using some other program that doesn't have the same equation editor, there's the video also shows you how to get it into your quiz. So some students don't like that I don't allow them just to write X bar, but the reason I don't do that is because we're in a college class and you should be able to figure out how to get something like that into a document you're editing. So that's, but I did create the video to help you with that. So take a look at the video if you're not sure how to get the symbol X bar into your quiz. All right, so this is just an example of how to do the mean, quick reminder, you add all the data values together and divide that by how many. Everybody, I think, is pretty much familiar with that. One interesting feature about the mean is if you put everything as a dot on the number line, and the number line itself didn't have any weight, but all of the dots had the same weight, then the mean is where that would balance. It's the balance point. So that's kind of interesting sort of characteristic of the mean. But basically it means that if you added all the distances above the mean and all the distances below the mean, that the distances above the mean and the distances below the mean would be equal. And here you go. That even shows that right here. Distances below the mean were 26 total. Distances above the mean were 26 total. All right. And the mean is the only measure center with this special property. And then there's a couple of examples. The other measure of center that we see a lot is the median. And the median is the middle value in a set of data. If you've got an odd number of data values, like in the median homework score example here, the median is going to be very easy to find because in here there was 9 values. It was the fifth, 1, 2, 3, 4, and 1, 2, 3, 4 from each end, and then the fifth in the middle from either end is the exact value of the median. You of course have to put them in order first, but if there's an odd number of data values, it doesn't show it there. If there's an even number of data values, there won't be an exact middle number, so we average the two that are closest to the median. That's all, of course, if we're doing it by hand. In general, we use the calculator to find those things. And there's also a video. You can get to all these things through the resources button, but there's a video that shows you how to calculate the mean and calculate the median using the calculator, as well as some other things that we'll be talking about shortly. All right. So here's some homework scores with an outlier. Most students did quite well because perhaps the homework is mostly graded on completion. But there was one student who refused to do any homework at all. And then they calculated the median and the mean for the set of data, and they're both in the B range. But if you look at the locations on the number line there, the median tends to be right in the middle of all of the data, whereas the mean tends to be below most of what the vast majority of the class did. And that's because the mean is much more affected by that outlier. So if there's an outlier, if there's outliers on one side but not the other, the mean is always going to be pulled in the direction of those outliers. The same thing is true of skewing, and that is, if there's a long tail in one direction, the mean is going to be pulled in the direction of that tail. We say that the mean is not a resistant measure center. It's not resistant to outliers, and it's not resistant to skewing. Those things heavily impact the mean. And in fact, when there's fewer homework scores, we can see even a bigger difference on how the outlier affects the mean and the median. And the same thing true here. This is home prices, I think it said. No, personal income, sorry. And it shows the median income and the mean income, and you see the mean is much higher. Any data set that's heavily skewed like this, we're almost always going to use the median as our choice of center. So we would talk about median income. You often hear about, median home prices. And if you hear the word average used, a lot of times it would have been better to use, if they truly did use the average, it would have been better to use the median. A good example of this, if you look, you could Google this quite easily, but I think a month or maybe 2 months ago, there was a news story about how they had done a survey and they found the average cost of weddings had gone up, was quite high. And in fact, let's just get that number for you. Here it is, 2014. There you go, March 28th. So it came out at the end of March. $30,000. It's a lot of money to get married, isn't it? But it says average. And there was even a story in one thing where they talked about how that it would have made way more sense to use the median than the mean, because let's say there were three weddings that they measured. Well, if one of them is $100,000 and one of them is $20,000 and one of them is $10,000, well, the average is high. I probably should have picked different numbers. It's divisible by 3 when you add them, but the average is pretty high, but the median is that $20,000 number. So one big expensive wedding can balance off a lot of less expensive weddings in this case. So when we have data that are heavily skewed, like something like income or home prices or wedding costs, for that example, for that matter, the median gives a better picture. Now you might wonder then, why then did they use the average here instead of the median? It's a good idea to look at who did it. Let's look at this one. It said right at the top, but you may be able to see it better when we go to the actual article. Can you hear me? Again? Sorry. I think I know why that happened. Yeah, that was my connection dropped out. Let me share my desktop again. So I believe we were talking about when my connection dropped out, the wedding. So what I was going to say was we were looking at this wedding survey, and it said it's a wedding study by the Knot, which is a wedding planning website. And I know for a fact that the median would be quite a bit lower than this number. So you might wonder why they would use the mean. Well, look, again, it's a wedding planning website. It certainly behooves them to encourage people to spend more on their wedding, not less. So you always have to look at the source of the data. And that's an important point. All right, we had someone else join us who's only going by their email, so I'm not sure what's your first name? Krista. All right, Krista, welcome. What we're doing right now, Krista, is we're going through the material in Module 2. We've already covered 2.1, which is the dot plots and histograms, and now we're into 2.2, which is mean and median, measuring where the center of quantitative data is. All right, so this is an example here again that shows that a right skewed data set can make the mean considerably higher than the median. All right, so this is the big point, the main point, as it says. Use the mean as a measure center only for distributions that are reasonably symmetric with a central peak. When outliers are present, the mean is not a good choice. Use the median as a measure center for all other cases. Both of these examples also highlight another important principle. Always plot the data. You always want to look at a picture of the data, no matter what. Always look at a picture of the data. Excuse me. And we got another applet here. Good grief, I'm not having trouble scrolling straight. All right. Oh, let's make it smaller. The applets don't like being zoomed in on. So this is just a chance for you to sort of play around with points and see how it affects the median, the mean and the median. So if I add a point here, add a couple points there, add a point there, add a point way up here, and you see the median hasn't changed yet because I have all those points at 3. So it's just a chance to sort of play around with data sets. So here now I've got a data set of 7 values. The median is 3 and the mean is bigger than 5. So that it's just asking you sort of, it's just a chance to sort of to play with it and see how a few values can change the mean more than the median. All right. So this is a picture of a data set. It says which measure of center is the best measure for a typical value in the histogram above. This one would be the median because it does have a, well, so they're saying both here. Median will always work, but if the mean works, generally we don't usually report the median as well. So, but in a symmetric distribution, the median will be pretty close to the center. All right. There is one place though where with a skewed distribution, the mean is a little better, and that's in data sets where there aren't too many values, but they're still heavily skewed. An example for that might be number of children in a family. Most families tend to have, there's more and more families, well, married couples that don't have children, so we might say most families tend to have 0, 1, 2, 3 kids, and after 3 you start dropping down, especially now. People tend to have fewer children than they used to. So 4, 5, they go down and down and down and down. So it would be a very strongly right-skewed distribution. You'd have a peak around 1, 2, 3 kids, and then it would trail off, but there would be still values at high numbers of children. They have reality TV shows about people with lots and lots of kids. So even though you might say, well, so we should use the median, it actually turns out in that case the mean is a little better because the median is just not fine-grained enough. It doesn't give you really an accurate enough picture. I could imagine the median number of children in a family in the U.S. is probably 2. But if we look at the mean, the difference between, say, 2.1 children per family on average and 2.3 children per family on average over the millions and millions of families in the country would mean a lot of kids in the country. So in that case, that's one case where the median actually might be a little better. I mean, the mean, sorry, might be a better number, where there's not so many different values. So 2.2 is pretty short. That's it for 2.2. There's sort of the key guidelines on the wrap-up page, and then of course your checkpoint. All right. Let me pause for just a moment in case there are any questions before we go on. Anybody got any questions for me? It seems to be fairly clear. Mean and median is, when is the first quiz? Wait a minute. The first quiz was due, the first pass quiz was due Tuesday night. Well, quiz 1 was due last Thursday. Quiz 1 was online. Quiz 2 was a Word document. That was due on Tuesday. And then there's quiz 3 and 4 due next Tuesday. All right. And remember that what I do. This is a. We'll make a quick pause real quick. Let me open up Blackboard real quick. All right. So if you go into Blackboard. If you go into our class, and I'll change it to a student view real quick. So, all right, so you see this. If we go, I'll always go to assignments. There's our week 2 assignments. And if you want a quick view of what's due and when, you click the checklist. And this tells you when I would expect you to have each thing done. But if you want more detail on what each thing is, then you click I clicked the same thing again. You click the details, and this tells you sort of the objectives for the week, and then more details on each of the assignments for the week. All right. So make sure you look at that each week, and then you'll know exactly what's due and when. All right. In 2.3, in 2.3, we're talking now about variability, and more specifically, to start off with, variability relative to the median. So if we're going to use the median, how do we describe, so spread is the same thing as variability. So at this point, when we're talking about numerical measures, actual calculations, so for center, we already talked about center, that was the mean and the median. For shape, well, for left skewed versus right skewed, you can think the mean gets pulled towards the longer tail. So if the mean is bigger than the median, you're probably looking at something that's right skewed. If the mean is less than the median, then you're probably looking at something that is left skewed. All right. Now though, we're talking about spread or variability, how much the data vary. When the data are all close together, there's less variability, less spread. When the data are farther apart, there's more spread. All right. So let's look at these two sets of exam scores. They have the exact same median, but it's pretty clear that Class B has more variability than Class A. In Class A, more of the scores, and even the overall range is exactly the same, but in Class A, more of the scores are close to the median, whereas in Class B, more of the scores are further away from the median. So what we want to do is figure out some way to describe that with a number. Okay. Well, the first number they talk about is the range, which is just the largest value minus the smallest value. And in both of these cases, the range is 55, 95 minus 40. So that doesn't really help us that much because it only uses the biggest and the smallest value. It doesn't take into account sort of the overall thing. So now what we're going to do is we're going to talk about something called the interquartile range. Now the first thing we do is we divide our data into quarters. That is 4 equal parts, if there are 4 equal parts. If there's not, we work with it as, we make them as equal as we can. So you see here, with the upper set, there was 32 observations, so that means the quartiles, the quarters each have 8 values, and with the lower set, there's 5 each. So there was 20, so there's 5 each. Then we go through that, and then the quartiles, we call them Q1, Q2, Q3, are basically the numbers that divide each quarter of the data. So between the first quarter and the second quarter is Q1, the second quarter and the third quarter is Q2, the third quarter and the fourth quarter is Q3, and then also we add to that the minimum and the maximum, and that gives us our 5-number summary. So that's what these are here. This is called our 5-number summary. And again, it's the lowest value, and then the number above the bottom 25%, the number be in the smack in the middle, which is also the median. Q2 is the median. Then the number that cuts off the lower 75% and the upper 25%, and then the maximum. So looking at Class A, maybe it's easier to see without the blue on it. We can say 25% of the class scored between 40 and 71. 25% between 71 and 74.5, 25% between 74.5 and 78.5, and 25% between 78.5 and 95. And it says, notice the second quartile mark, Q2 is the median. So some quartiles exhibit more variability in the data, even though each quartile contains the same amount of data. So some of the divisions, some of the 25% are wider than others. And then how do we measure the variability using it? Is by something called the interquartile range. And that's just, as it says, the IQR for short is Q3 minus Q1. What it tells us is it tells us how the width of the middle 50% of the data. or how much the middle 50% of data varied. So for class A, that came out to 7.5. For class B, it came out to almost 4 times as great, or 28. The middle 50% of class in A were in a very narrow range. The middle 50% of class in B varied quite widely. There's a pop-up example for the 5-number summary. Most of the pop-up examples like that, for things like the 5-number summary and histogram, will walk you through how to do it on the calculator. I also put a video up for how to do it on the calculator. The videos I put up online are on YouTube, that you can get to again through the resources button on Blackboard. Those are mostly linked to the in-class notes. Those in-class notes are also posted on the same resources button in Blackboard. But this can reinforce that as well if you click that pop-up there. So it's got TI instructions. You can see the data set here. So you can go through, this is the Best Actor Award winners, go through all that, put those numbers, the ages, in your calculator. I'm not going to do that right now. And then it'll give you the instructions right back here for how to find the 5-number summary. It shows you all the stuff that the calculator displays. All right. Oh. All right. And then there's a did I get this based on that as well. All right. Now another thing. So now we've got a numerical measure of center, the mean or the median. We've got a numerical way to think about spread, which is if the mean is higher, it's probably skewed to the right. If the mean is lower, it's probably skewed to the left. And if they're fairly close, the mean and the median, then it's probably pretty symmetric. And now we have a numerical measure of variability in the interquartile range. We'll look at another one in 2.4. But another good thing is we are going to now look at a numerical way to determine outliers. Before, we just kind of had to use a judgment. That looks far away from the other points, so I guess it's an outlier. Or, well, no, but then you might get into an argument over, one person says, I think that's an outlier. The other person says, well, I don't think it's quite far enough out. So what we want to do is we want to figure out a concrete way to determine outliers. And this is the way we do it. We take our IQR. We multiply it by 1.5. We take 1.5 IQRs. We go above Q3, we go below Q1, and any point outside of that range is considered an outlier. Sometimes I call those numbers the fences, these Q3 plus 1.5 times the IQR, and Q1 minus 1.5 times the IQR. So what we're saying by this is we're saying, okay, Q1 to Q3, that's the middle 50% of our data. Okay, that's the heart of our data. Clearly there's no the outliers are beyond that. How far beyond that do we get before we start saying a point is an outlier? Well, we take the distance between them, the Q1 and the Q3, that's the IQR. We multiply it by 1.5, and we go that far above Q3 and below Q1. If we're past that, we're an outlier. Okay. So here they talk about a visual example. Here we've got a data set. We've got our Q1 located there, our Q3 located here. And so we take our IQR, multiply by 1.5, go that far above Q3, that far below Q1. Anything past those points is an outlier. So we got 4 dots above Q3, above the upper fence, what I call that. Those are all outliers. Only one value below the lower fence. And that one is also an outlier. So there's 5 outliers altogether, 4 high outliers and 1 low outlier. Okay. And then some exercises, and then a summary of that information in a nice compact way. All right, let's see here. All right, now here we're going to start looking at an actual graph of the 5-number summary, which is called the box plot. So here are our exam scores again, and here are what we call 2 box plots for the exam scores. Now they've got the box plots right on top of the dot plots, so let me explain what we're looking at here. Basically the box in a box plot represents the middle 50% of the data. So the bottom end of the box is at Q1, the top end of the box is at Q3. That's the middle 50%. There's a line in the middle of the box. Oh, we lost someone. The line in the middle of the box represents the median. Oh, and she's back. The line in the middle of the box represents the median. And then beyond that, we have a tail, and the lower one, the tail goes out to the maximum on the right-hand side and out to the maximum on the left-hand side. But in the upper box plot, the tail doesn't go all the way out to the maximum exam score. What it goes out to is it goes out to the last number that's not an outlier. So this exam score right here looks like about 85. That's not an outlier. But this exam score of 90, that is an outlier. And this exam score of 95, that is an outlier. And we just put a little mark there, a dot, or this is an asterisk here. But and then on the other side, the lowest exam score that's not an outlier is 60. And then we had two exam scores that were outliers. It looks like about a 55 and a 40. So in the lower one, there were no outliers using the IQR times 1.5. But in the upper, in the other class, with the more compact middle 50%, there were 4 values that were outliers. Okay. And as it says, we so these are what we call side-by-side box plots. It's a way to compare the distributions. Sometimes, as this says, we draw them vertically instead of horizontally, but it's the same picture, just put vertically. So your calculator, in addition to some other things, you can have a box plot where the lines ignore the outliers. So in this case, the lines would go all the way up and all the way down, or you can have it show the outliers. On the TI instructions that I give you in the video for making a box plot, I do it with having you show the outliers, but it's a very easy choice when you take a look at that. All right, so here they just walk you through making it by hand. You can watch the video. It's pretty straightforward, but by and large, we would, it's only 3 minutes long, but we would, generally speaking, we would make a box plot using technology. And then here is even one in this what am I doing? There's one with 3 side-by-side box plots. Oh well, they're doing that because they want you to figure out which one comes from that histogram. And the way you would think about that, by the way, is if you look at that histogram, you think about the shape of the histogram, and then you look at those box plots and you think which of those box plots has the same shape as the shape of the histogram. All right. And then the did I get this and the pop-up, I imagine, will also, in addition to giving you some more practice, might also show you how to do it on the calculator, or there might be one further down. This, by the way, is showing you that you can end up with the exact same box plots from different data sets. So the box plot really is it compresses the data in terms of it's got 5 values, and so depending on the data set, you could get to those same 5 values in several different ways. So be careful of looking at one thing and thinking you know everything about the data. Just looking at box plot doesn't tell you everything there is to know about the data. All right. And then here is another applet where you can play around with things and see how it affects the box plot. All right. And this is just about comparing distributions. Here's a comparison between Best Actor award winners and Best Actress award winners based on side-by-side box plot. This also shows you how to do box plots on the calculator, and then this compares. So there actually is an example, I think, perhaps on the test where I asked you to make a comparison based on box plot. Your comparison doesn't need to be this long. This is actually talking about how you would do it. But this is really the paragraph you need to look at in terms of writing a good comparison of 2 distributions based on a box plot. This last paragraph before the example. Here's two box plots. Pittsburgh and San Francisco actually happen to have fairly similar median temperatures throughout the year, but notice that in San Francisco there's a lot less variability over the year than there is in Pittsburgh. It tends to get considerably hotter in the summer and colder in the winter in Pittsburgh than it does in San Francisco. But in the middle, they tend to be about the same. There's the one. I think the last one, the one by doing, is the one that shows you how to walks you through how to do a box plot on the calculator. All right, and then we're on our wrap up with the summary and the checkpoint for 2.3. So just one last topic to go. Let's see where we are time-wise. 9:48. We should be all right. Just finish it, wrap it up. All right. So I know this has been a long one, and next week's module will be similarly long, but after that, the modules should be a little bit shorter when we cover them on the Thursday webinars. Okay. So now we're going to talk about what if we use the mean for a measure of center. Then it doesn't make as much sense to talk about the IQR because the IQR is based on the median. All right. So here's a simple set of data, and they calculate the mean is 5. And then they give you a dot plot with the mean marked. In this case, the mean happens to also be equal to the median. That's just kind of coincidental to this particular data set. And we see, as it says, some data is close to the mean, some data is far away from the mean. And what we can do is we can calculate how far each thing is from the mean. And it also makes sense to use the sign to tell you whether it's below or above. So like we had, there's two -3s here at the top of this table. Let me make it bigger. And what that means is there was these two values of 2 right here were both 3 units below the mean. So their deviation, we call that the deviation, is -3. And then points with positive deviations are above the mean. And then there's pictures of the deviations. The blue ones would be negative deviations, the green ones would be positive deviations. Okay? And so they're asking you to calculate deviations for some values on these dot plots. That's pretty straightforward. So one thing they do then is they take the absolute value of each of those things and then average them together. And then you can say that the average deviation from the mean is 2 units. So on average, the points are 2 units away from the mean. I'm not going to spend a lot of time on this, on the average deviation from the mean. You can go through this page, and there's maybe 1, maybe 2 questions on the checkpoint. There's none on the quiz, and there's none on the test. It's not a very commonly used measure of variability. We're actually going to use the one on the next page. Yeah, so all of this is on average deviation from the mean. Yep. See if I can get it. There we go. All right, but what we're more interested in is what starts on the second page, which is standard deviation. Okay. Standard deviation has some more useful properties, and it's much more commonly used. What they do, instead of taking the absolute value with the deviations from the mean, we actually square each of the deviations. That also has the effect of making the negative ones positive. And then we add them, add those square deviations together. But this is where it gets a little bit counterintuitive. We don't divide by the number of deviations, we divide by n-1. N, by the way, in statistics, I didn't mention this before, is how many observations you have, or sometimes we call that the sample size. So instead of dividing by 7, which is the number of deviations I had, I actually divide by 6. And then lastly, we sort of, to account for the squaring, as it says, we take the square root at the end and we get 2.58. A little bit bigger than the average deviation, but it's pretty. But what we do is we can say that it represents the typical distance from the mean for values in the data set. And then it's, again, as this shows, is 1 standard deviation to the right and the left of the mean. Here it is as a formula. I don't expect you to know this. You would do the standard deviation using your calculator if I wanted you to find the standard deviation of the data set. And that also is in the video, so I go through it step by step in the video. All right. and this just sort of walks you through what the formula says to do. But basically, you take all the deviations, you square them, you take all the deviations, which is the x minus x bar, you square them, you add them, divide by n minus 1, and take the square root. That's all that formula is telling you. It's just basically putting in a formula what we did before, right? But really, more what I want you to have is sort of an intuitive sense of what standard deviation is measuring, and it's measuring how far typical data values are from the mean. But more generally, it's measuring how spread out the data are. So when we look at these two distributions, and it says which set has the larger standard deviation, we would say the adults do, because the adult cereals have the larger standard deviation because there's much greater variation in calories for the adult cereals than there is for the children's cereals. Now it says approximate the standard deviation for the children's cereals. Now this is kind of tricky because you haven't done much practice, but notice, I mean, here's the center's around 110, and most of the values are right there, are no fewer or 10 away, and there's only one that's a little further. So in this case, 6.5 of these three choices make, and 0.75 is way too small. 13.5 is probably too big. 6.5 makes the most sense. The adult one is a little trickier. What you want to do is kind of estimate, okay, so from 100, about how far out would I go to get typical values of these. 40 is probably too far. 55 is even further, so 23 makes the most sense there. This is not something I would ever ask you to do without kind of multiple choices, where one is definitely the most obvious choice. One of the answers is the most obvious choice. In general, though, with a data set, I would have you do it by using your calculator. And then that's what this, using technology, that's what this last example is here. You would go in there and it's a pop-up. But like I said, there's also the video that shows you how you get the standard deviation. All right, so what we know about standard deviation is a measure of spread. It's pretty close to the average deviation from the mean. We can say the mean plus or minus the standard deviation gives a range of typical values. And generally speaking, we're going to use the technology, not calculations by hand, to calculate the standard deviation. All right, so now we're going to, let's look at standard deviation. So it says these histograms show the backpack weight carried by two groups of school children. One is a group of 1st and 3rd graders. The other group is 5th and 7th graders. In each histogram, we mark the mean and the standard deviation. So note that the mean weight for 1st to 3rd graders, 1st and 3rd graders, I guess, is about 6 pounds. And then you see the standard deviation there. It's a small purple number of 2.1 pounds. And then for the 5th and 7th graders, they have backpacks that are more than twice as big, over 14 pounds on average, with a standard deviation of 7.2 pounds. All right. And then they give you shape. They're both somewhat symmetrical with a slight skew to the right, particularly in the second distribution. The mean is 5.8 pounds. Standard deviation is 2.1 pounds for the 1st and 3rd graders. Typical range of values about 3.7 to 7.9 pounds. And then they go with the 5th and similar things with the 5th and 7th graders. All right, so and I wouldn't worry too much about these graphs here. It's just, again, sort of using the standard deviation to examine it. This is, again, kind of looking at data sets and kind of trying to have an intuitive sense of which would have more variation. This exercise is whether you'd expect to see more variation among competitors at the Olympics or among competitors in high school meets. Now, the number of individuals doesn't matter. What matters is how spread out their times would be. And in general, even it is the case in this case that the high school meets would have the greater standard deviation, because you expect fast high school students to be much, much, much faster than slow high school students. But even slow Olympic athletes are probably still pretty darn fast. So there's not going to be as much variation among the Olympic athletes as there would be among high school track and field competitors. can two data sets have the same mean but different standard deviations? Sure. They can be centered at the same place but have different amounts of variability. They can have different means but the same standard deviation. They can, and this applet helps you follow that. I minimize the picture again so we can see the applet. So it asks you it says some activities to work with that applet. All right, let's move on. So these are some different data sets. I'm trying to predict which one seems to have the greatest spread from the center, the greatest variability. Similar on those. Let's see here. So I think we're on the last page here. How do we decide what measurements to use? Well, you sort of go with the same thing we said for mean and median. If you use the mean, use the standard deviation. If you use the median, use the IQR and the 5-number summary. So if you have data that are skewed or contain outliers, that's when we use the median. So then we would also use the IQR and 5-number summary. We have, so median for center, IQR for spread. But if the data are reasonably symmetric, then we can use the mean for center and the standard deviation for spread. That's how we decide which measurements to use. Let's see here. And this is just some examples on that where these are some heavily skewed distributions where it makes more sense to use the median and the IQR than it does to use the mean and the standard deviation. I lost one person there. All right, and it's just some more practice thinking about when to use which one. But in general, like the mean, outliers can have a very strong impact on the standard deviation. An outlier will greatly increase the standard deviation, but it won't have a huge impact on the IQR. So one value can greatly increase the standard deviation, and a big part of that is because it's squared. Because if you think about two values, one is 5 away from the mean, and the other is 10 away from the mean. Well, one is twice as far as the other, but then when you square them before you add them together, you get 25 and 100. 5 squared is 25. 10 squared is 100. So all of a sudden your one that was twice away has twice as far away has 4 times as much impact on the standard deviation because of the squaring. All right, and then we have our wrap up for 2.4. You can go through that. But one last thing I want to point out in the Module 2 review is that one assignment for this week is this lab exercise for drinking habits. If you click it, it'll bring up a pop-up, and it'll load something called the Stat Tutor. And basically what it's going to do is it's going to walk you through some exercises based on a data set. My recommendation is to do this using Excel, or you may be able to open it in a similar word processing. You might be able to use the, not word processing, I'm sorry, spreadsheet. You might be able to use the spreadsheet on Google Docs, but that might be a little bit trickier. But this is one of the assignments for this week, is to go through this. I will say here, although perhaps people who don't watch the video won't know this, I don't generally grade this. What I do is I keep it, I go back and check to see who's done it. And when I end up with situations where students fall just below a certain grade, and I have to decide whether to move them up, one of the things I can look at is something like this that was an assignment that wasn't actually graded. And if the students are doing that and putting forth those efforts to gain a greater understanding of statistics, then I would be more likely to bump that student up to the next grade than I would for a student who neglects to do those sorts of things. So if you have an 85, it probably won't matter that much whether you did this or not. But if you have a 79, then it probably would make more of a difference. All right, that was long, I know. Before we sign off, though, are there any questions of the material? And of course, even if you don't have them tonight, you can post them to Piazza. We haven't had any questions posted to Piazza yet. but you can post them to Piazza. I can answer them there for everybody. I will be back on Monday night next week, even though the homework's not due till Tuesday. But I'll be back on Monday night to answer any questions that people have. Jonathan's good. Oh, you know what? Thank you for asking that question, Kimberly. I forgot to put up a group button on Blackboard, but I'll do that right after we get off the call. There is another way to get there through the tools link on Blackboard, but I'll put a direct link to the groups on. I'll put a button on the left-hand side in Blackboard. Thank you. What do you mean in terms of the tentative schedule? Oh, you mean like the assignment list, the checklist and all that? That I will post that on Monday at the latest next week. This week it's supposed to go up on Mondays, but this week it was a little bit delayed, which is why I pushed the homework due date back to Tuesday for next week. But in the following weeks, the assignments will go up on Monday and they'll be due the following Monday. Oh, that was up the first day of school. Quiz 2, those assignments have been up since the first day of school. So you got to make sure to check under that assignments button. But one quiz, there'll be 3 dropped quizzes over the course of the semester. So if that's the only quiz you miss, then you should be okay. And in fact, since you're on the call, and I haven't posted the answer key yet, if you can, oh yeah, weird. If you go back to the week 1 assignments, do quiz 2, turn it in. There's nothing that blocks you from turning it in. I'll go ahead and grade that for you. That's your bonus for being on the webinar tonight. But turn it in by tomorrow. Kimberly, anything I can do for you? Are you good for the moment? Yes, if you click the group link, it will take you, you will be able to go onto your group page, yes. And that will have the names of your group, and you'll be able to share your version of the document with your classmates who all have the same thing. I mean, your group mates who all have the same thing. Every group has 5 members. There'll probably be some who may not participate. You may hopefully end up with hopefully you'll end up with at least 3 total people who participate. And then after the first one, anybody who doesn't participate gets put in a group with other people who don't participate. So hopefully, the first one is always kind of a crapshoot as far as putting people together. All right, if that's it, then I'll bid you good night, and I will go ahead and put up that group link. I'll post the link to the video, although you guys were here, Kimberly, you could watch the beginning of it if you wanted to. And I'll talk to you soon. Take care.